All right, so last time we finished with the example, we were looking at finding the inverse. So we actually found the inverse of two log functions. And so today we're going to continue with that, and then we're going to look at solving some equations with logs and exponentials. So I want to continue on with finding inverses. So we kind of race through that at the end. So make sure that I do the, yep, so we did the 2 to the x plus 7, and then 6e to the x plus 4 plus minus 9. Does that sound familiar? Okay, cool. All right, so let's look at finding the inverse of logarithmic functions. So if we have g to the x equals the log of x minus 11 plus 8, and we want to find the inverse of this. So just like we always do, we're going to rewrite the equation, right, swapping x and y, and then we're going to solve for y. So if this is y equals all of this stuff, right, now we'll say x equals log of y minus 11 plus 8. So if we solve the new equation for y, then that should give us the inverse of g of x. So the first thing I want to do is I need to get this log by itself. So, right, so we're going to subtract 8 from both sides. And then here's where you kind of have a choice. So we need to get the y from outside of the log. And so one way we can do that is we can eliminate the log if we raise it over its own base. So in this case, since it just says log, we know that's base 10. So I need to raise each side of the equation over 10. So this becomes 10 to the x minus 8 equals 10 to the log of y minus 11. The left side, nothing can really change here, but on the right, the 10 now eliminates the log, and I just get y minus 11. So what we've done here is we basically plugged the function into its own inverse, right? The inverse of log of x is 10 to the x. So then to get the y by itself, right, we're just going to add 11 to both sides. And this is now the inverse function. So I can tell you that the number one incorrect move on this problem would be right back here. Somebody would see log, they would try to raise both sides over 10 right here, and they would try to distribute the 10 all the way across. So they would tell me 10 to the x equals 10 to the log plus 10 to the 8, and that is wrong. You have to isolate the log by itself in the same way you have to isolate the radical, right, before we square both sides to get rid of it. You need to get that log on all by itself on one side of the equation, then raise it over its own base, and then you're allowed to do that. Do I see the difference? Okay. So you just have to know when you're allowed to make these moves and when you can't. All right, so let's look at another one. So now we have 21 natural log of 2x minus 4 plus 9. So the first step is always the same. We're simply going to rewrite the equation, flipping the x's and y's. And then we're going to solve this for y. So I definitely need to subtract the 9 first. If I try to divide by the 21, right, and then I have to divide the whole thing by 21. So we're going to subtract 9 from both sides. And then I can divide both sides by 21. Oops, that's a y. Now I actually had another option here. Instead of dividing both sides by 21, I could have moved the 21 in as an exponent. I could have said, well, this is natural log of 2y minus 4 raised to the 21. And that might actually be cleaner in terms of notation, because now my next step is going to be to raise everything over e, because natural log is log base e. So I'm going to have e raised to that fraction, right? So I kind of see now that that's going to be kind of gross. So I'm actually going to back up a step. So everything was fine that we did, but let's back up a step just to make the notation nicer. And let's actually move the 21 in as an exponent. So there's always more than one way to get to the answer, but this is just going to make things a little bit cleaner to write. So now that I have that natural log term by itself with no coefficient in the front, I can raise it over its own base, and its base is e. So I'm going to simply raise both sides over e, and we'll get e to the x minus 9 equals 2y minus 4 to the 21. So now I'm not really stuck, but I can't get the y out of that term unless I do something. What do I have to do? Take the 21st root. So this is the dilemma that we were in, right? We could have divided by 21, right? That would have created a denominator in that fractional exponent, right? Or we could have moved it inside thinking we were going to be clever. Well, when we moved inside to be clever, yeah, it was nice and neat to write, but now you have to take the 21st root, and when you take the nth root of something, it just turns it in the denominator, so you're going to end up right back here anyway. So, right, and the same thing as the square root is 1/2. Right, so really what we did was we raised it to the 1 over 21 on both sides, and that's what happened. So we were actually on the right track originally, so you want to make sure you understand that even though you have multiple moves, sometimes you're going to end up circling back and doing the same thing anyway. All right, so now we want to get y by itself, so we're going to add 4 to both sides. Please notice here that when I'm writing my fractions, I'm using a horizontal bar. Don't use a slash. Those days are over, because when you get into calculus and the denominator starts to get complicated, if there's an expression in the denominator, I can't tell what's in the denominator and the numerator, so make sure we write our fractions. All right, and so then we could divide this whole expression by 2, or I could simply multiply everything by the 1/2. And now I have the inverse function. So in these last two problems, you had to know the base. It wasn't explicitly written. And those are the only two types of logs where the base is implied. Any other base that we want you to work at, we'll actually have to physically write it in the same way square roots are implied to be 2. We write the number if it's anything other than a 2. All right, any questions over these? Mm-hmm.
If we were to just do divided by 2, I wouldn't
be fine.
Wrong.
No, that'd be fine. I just was trying to keep from writing another big old fraction, so just make it even look grosser. Yeah. Mm-hmm. Also, I saw the 4 was divisible by 2, so that's why I kind of sneak peek ahead. So when you're doing your algebra steps, always, you couldn't just blindly do the algebra, but you can also sometimes peek ahead and kind of get a sense of what's coming, and you can make adjustments once you've done a ton of these. All right, so what we're going to do now is we're going to solve some expressions involving logs, and then we're going to look at some exponential expressions. So we want to solve these equations for x. So there's actually a rule very similar to, like we said, if we have b to the n, right, raised next equals b to the m, and the bases are the same, we can actually set the exponents equal to each other. So there's a similar property for logs. If you have log base b of some expression m, and that equals log base b of some expression n, then m must equal n. Okay, so if it's log of the same log with the same base of different expressions, then those two things have to be equivalent, or else they're not going to be equal to each other. So that's a handy tool that we can try to use wherever we want. So here we have the same base. So if I can get rid of the coefficients, which I can easily do by moving them inside as exponents, right? We can say log base 4 of x squared equals log base 4 of 5 cubed. So now I have log of base 4 of some stuff equals log base 4 of some different stuff. So now I can just pull the insides out and set them equal to each other. So now I can say, well, that means that x squared has to equal 5 cubed. And so 5 times 5 is 25, and if you multiply by 5 again, you'll get 125. So this is just 125. So now if I take the square root of this, technically speaking, algebraically, it should produce two answers, right? Plus or minus the square root of 125. But you need to go back when you're solving a log expression and verify that your final answers work in the original problem. So if you go back to the original problem, the x is just sitting by itself in a log, and logs do not accept negative numbers and do not accept zeros. So negative square root of 125 is going to have to get kicked out, and we're only going to accept the positive value.
Even though it's going to be squared?
It's not squared. You have to go back to the original equation and look at how that is structured and check that. Now, if it were log base 4 of x squared, if that were the original equation, sure, we'd be fine. But the original structure, because whoever wrote this expression did not want it to include that value. Yeah. So generally, the way I've seen, like even on online homework systems, as long as it can be plugged into the original equation you were given, it'll accept it. If not, you have to kick it out. Yep. And so it's not going to be an always situation where you can always throw out your negative numbers. Sometimes those negative numbers will be okay based on how the original equation was structured. If we have multiple x's in the equation, just like with domain, if any piece of the equation kicks it out, then it's out for the whole thing. So if it's okay in one part for one x but not okay for the other x, it's gotta go out for good. So I'd really like to be able to use my rule, right? I have natural log on both sides, but I have to simplify it down to one single log term on the left and one single log term on the right. So the right's fine, but for the left, I need to combine those two expressions into one term. And so when we add, what do we do on the inside when we combine? Multiply. So that means the left side of this is become the natural log of x squared plus 4x, and that will equal the natural log of 12. Since I have log of the same base, right, I can now just simply pull the insides out. The other move you could make is you could say, well, I'm going to raise both sides over e to cancel those logs, but that's just an intermediary step. You end up in the same place. You're just setting the exponents equal to each other. So we're going to have x squared plus 4x equals 12. This is a quadratic, so we got to move the 12 over to the other side. And if I multiply 2 times 6, I get 12. And if you add 2 times 6, you get 12. But the issue here is this means the signs of my numbers should be different, right? Or sorry, if you subtract 6 and 2, you get 12. So I need to have a positive 4. So I'm going to say x plus 6 times x minus 2. So now positive 6 times negative 2 gives me negative 12. And positive 6 plus negative 2 gives me positive 4. So this works. So I get two answers here. I'm going to get negative 6 and 2. But if you go back to the original equation, well, natural log of x won't accept negative 6. And furthermore, natural log of x plus 4 won't accept negative 6 either, because negative 6 plus 4 would be negative 2. So negative 6 is out, and the only valid solution is 2.
On the test, would we have to like write out if we'll accept negatives or just cross it out?
No, if you did something like this, if you found the answer and you actually crossed out the ones that didn't work, like I would be able to tell why, like that's good enough for me. Just kicking it out because it's not in this domain. But yeah, that's fine. Yep. But I would like to see, like in your algebra, I want to see that those are the solutions for this algebra, and then it's okay if you throw them out, you know, and you kind of circle the final answer. Yeah, it's fine. Yeah.
So you can't take the natural log of the negative number?
Nope. And so the 3 rules I gave you for domain, right? No zeros in the denominator, no negatives under even roots, only positives inside logs. So positive numbers mean no zeros and no negatives, because 0 is neutral, right? So this one's a little bit different because I don't have logs on both sides of the equation. I could theoretically move one of these logs over to the other side, but it's not really going to do me any good because I have that -1 just sitting there by itself. So what we want to do now is we still need to combine all the logs into a single term so we can eliminate them by raising it over its own base. So on the left side here, because we're subtracting, this becomes the log of x minus 9 divided by x equals -1. And now to get rid of the log, I have to raise it over its own base. So log by itself is base 10. So we're simply going to raise each side of the equation over 10. So on the left, right, that cancels the log. And on the right, I get 10 to the -1, which is really 1/10. So now if I want to finish this equation, right, I can just cross multiply. So on the left, I'm going to get 10x minus 90 equals x. And so 9x will equal 90 because I subtracted x from both sides, added 90 to both sides. And x equals positive 10. And that solution, that answer is fine because if you go back and check, 10 minus 9 is 1, and 10 works fine in the log, so we can keep that answer. If we had had, let's say, -10 as our answer, then the answer would have been no solution, right? We would have to kick out any answer that we got. So 10 worked fine. And I had to check both places to make sure it was going to work. All right, any questions on this? Okay. focus. There we go. All right. So this one has a similar structure to the last problem, but instead of dividing it to create a fraction, we're going to have to multiply the terms on the left because they're being added together. But we still can't use our previous rule. We're still going to have to combine everything first. All right, so we're going to have to multiply those two terms together. And if I want to eliminate that log, what do I raise both sides to? 3. So we'll raise both sides over 3. That will eliminate the log. So on the left, I'm going to get x squared plus 12x plus 35 equals 3. So all I did was FOIL these two terms together. So once again, I'm going to have a quadratic, so I need to make sure it's set equal to 0. So the next step is going to be to subtract 3 from both sides. And 4 times 8 is 32, and 4 plus 8 is 12. So this will factor into x plus 4 times x plus 8. So -4 and -8 are my answers. So if we go back and check, well, -4 works fine in the first expression because -4 plus 7 is +3. -4 plus 5 is +1, so -4 is okay. We can plug that in. -8, however, gives you -1 and -3, and so -8 does not work. So only -4 we keep. So don't assume that you can never have any negative solutions. It's just those negative numbers can't produce any negative results in the expressions, right? So if we had log base 3 of just x in this equation, then both answers would have had to be kicked out. But because we had other numbers being added that kept it positive, we were allowed to keep the answer in the equation. And so hopefully you guys can see why we had to do the last unit before we can do this unit, because things like quadratics come back. Some of the algebra we need to use, it just kind of builds. All right, so we have another natural log. And this one I can tell you is one that for some reason, when you guys get on tests, students just don't like it because it doesn't clean up nice and neat like the previous problems we've done. But you just keep solving anyway, all right? So on the left side, we're going to combine these, and they're being divided, so we're going to get the natural log of x over 4 minus x equals 7. And I'm going to raise both sides over the base, and the base is e in this case. So we'll raise this to the e and this to the e. So on the left, all I'm left with is what was inside the log, but leave it e to the 7. That is the exact number. Don't put it in your calculator and try to estimate it, all right? So now what we're going to do is we need to solve this for x. So I'm going to multiply both sides by 4 minus x. And then in order to combine these two x's, I need to distribute the right side out. So I'm simply going to get 4e to the 7 minus x e to the 7. And then I want to get everything with an x over on one side. So since this guy's negative, I'm just going to add that term to both sides. So x plus x e to the 7 equals 4e to the 7. Then on the left, I can factor an x out. And to get x by itself, we simply divide by all this stuff. So these aren't pretty, but that's the correct way to do it. It's just, E is just a number, so you just work with it like you would any other constant, all right? Now, in terms of verifying this answer, well, if you look back at the very beginning, right, well, x cannot be a negative value, and e to the 7 will never be negative, right? So we have a positive number in the numerator here. We have a positive number plus a positive number, so this is a positive number. This is not a problem, right? And then the only other maybe issue would be, well, is this number less than 4? Because if it was smaller than 4, then it wouldn't work on the other piece of the equation. But we can kind of see here that it's not going to be smaller than 4. Because E is about 2.71, right? And we just raised it to the 7. So 2 to the 7, I think, is 128 or something like that. So 3 to the 7 basically is, would be even bigger. Then you multiply it by 4, and then even though you divided it, it's still going to be much, much bigger than the number 4. So we're actually going to be fine here, and this would be your answer. And we're usually pretty kind. We're not going to give you a problem where the answer comes out to be something like that and it not work, because you would have to easily be able to see that it doesn't work. But what you should know is that this is definitely a positive value, because e to the anything is going to be positive. All right, so let's go a little crazy. So in this problem, I have log base 2, log base 3, and log base 5. But if we whittle it down, we're going to see that this is actually very doable and not so bad. So the first thing that I would want to do is let's get the two log base 2's over to the same side of the equation, right? Because we know we could combine those if we needed to. So I'm simply going to subtract log base 2 of x minus 3 from both sides. All right, so that just moves that guy over to the left. Then what is log base 3 of 9? 2. Log 9 is 3 squared. Oh, sorry. There we go. So 9 is 3 squared. So log base 3 of 3 squared is just going to be 2, right? It just drops the exponent down. So I'm just going to, right, log base 3 of 3 squared, right, equals 2. So this guy is just 2, right? What about 5 to the log base 5 of 3? It's just 3. So now on the left side, I can combine these two logs. So we've got x plus 3 divided by x minus 3, and all of that equals 5. And now I can raise both sides over 2 to eliminate the log on the left. So x plus 3 divided by x minus 3 equals 2 to the 5th, which is 32. If you left it as 2 to the 5th and through all your algebra, I would be fine with that, but it's just probably easier to work with 32. All right, so now in order to solve this for x, I need to multiply both sides by x minus 3. And then I'm going to distribute my 32. And so subtracting x from both sides gives me 31x. Adding 96 to both sides gives me 99. And then when you divide 99 by 31, I don't think that's pretty. So I think you're just stuck. And that's definitely a number bigger than 3, so we're okay. So even if they look kind of gross and yucky at the beginning, go in and dissect it, but we were able to turn 2 of those things into constants right away, and then the problem became way more manageable. So the idea is you want to combine the logs with the same bases at the beginning of the problem. All right, any questions over this one? No. All right, so now we're going to switch gears and we're going to look at some expressions solving for x where we deal with exponentials. All right, and we kind of already saw some of these on the Monday lecture that I did, but I want to go through a few more because some of these can get nuanced. So one of the things that you want to get used to when you're working with exponentials is if you have e to the 3x, what you really have is e to the x cubed, because when you raise a power to a power, you multiply them together. So if you saw e to the 2x, we know that's e to the x squared. So what's happening here is I have essentially e to the x cubed minus 16 e to the x. So I can actually factor an e to the x out front. So if I say this is e to the x, well then now this is e to the 2x minus 16 equals 0. And so now what I have inside those parentheses is I have a difference of squares, because I have e to the x squared minus 16, which is 4 squared. So this factors again into a plus b, right? A minus b. Where a is e to the x, like if you FOIL that back out, you'll get right back to that. So now that we've factored as far as we can, right, the next step says, well, use the zero product property. It says, well, you set each one of these pieces equal to 0 and see what values of x would make it 0. So here's what would happen. We'd get e to the x equals 0, right? Or e to the x plus 4 equals 0. Or e to the x minus 4 equals 0. I'm just going to drop this guy down for a second. And so this would mean e to the x equals negative 4, or e to the x equals positive 4. So for any value x that makes any piece of this 0, then the whole thing would become 0 because you're multiplying everything together. So we have a problem here, and this is where knowing your domain and range is important. So what is the domain of an exponential? Well, it's all x, right? But what's the range of an exponential function? 0 to infinity, but 0 is not included. 0 is an asymptote. So e to the x can never be 0. This is a completely false statement. That'll never be true. So what we're really saying there is this piece of the equation will never be a problem. That's never going to be the thing that makes it 0, okay? Then we have e to the x equals negative 4. Well, that's also false because the range of e to the x is 0 to infinity. E to the x can never be a negative value, right? So this is also false. So this is telling me that this piece of the equation can never give me a 0, no matter what x I plug in. So now it's all up to this guy, okay? So e to the x could absolutely be 4, okay? So now we got to figure out, well, what x value could make it 4? So instead of raising it over the base with logs, now we want to take the log of both sides to eliminate the e. So in this case, I'd use natural log. So we would say, well, natural log of e to the x equals the natural log of 4. On the left, the natural log takes out the e. And so there's my final answer. So there is only one solution to this equation. So whenever you see an exponential, just some a to the x equals a 0 or equals a negative value, that's false, because that will never come out of the range of that expression. Yeah. All right, any questions on that? Yep.
How do we know we're looking at range and not domain?
Well, in this case, you're looking at range because it's the result of a to the x. The results are the y values, right? So it's saying that, and you know, we know that any x could go in. We know that it's possible that any x could come out when we solve, right? Because that would be the values you put in. But when you get to the situation where you have e to the x to the 0, because think about what the next step of algebra would be in both of these. You would have taken the natural log of both sides, and you would have seen natural log of e to the x is x, but you can't take natural log of 0, right? Here, you could have taken natural log of the left, but you can't take natural log of -4. So you should have picked it up in the next step if you tried to go further, but you can't do that, right? It's like trying to take the square root of a negative number. You're not allowed to do it. Yeah. And it's okay. If you had gotten to that next step and said natural log of -4 and then shut it down, that's fine. But eventually you should have gotten to a point where you see that that's a false expression. And all of you are going to see that at kind of different places. And some of you may have even picked it up back here. You know, I mean, that's fine because you knew the next step would be to set each piece equal to 0. But as long as you demonstrate to me in some way, shape, or form that you're throwing it out, I'm okay with you throwing it out as long as it's valid. Just notate that you're tossing it out, you know, in some way, like by crossing it out or something like that. All right, so let's look at another one. So once again, you need to think of e to the 2x as e to the x squared. So this is actually just a quadratic. It's e to the x squared minus 8 e to the x plus 15. So this thing will factor like any other quadratic. So e to the 2x will only factor into e to the x and e to the x, right? But we need to figure out what will components of 15 will make up 8, and so that's 3 and 5, right? 3 times 5 is 15, 3 plus 5 is 8. So I can factor this. E to the x minus 5 times e to the x minus 3. So then if I set each piece equal to 0, I'm going to get e to the x equals positive 5 or positive 3, which is perfectly fine. And so then taking the natural log of both sides gives me that natural log of 5 or natural log of 3 our solution. So we actually got 2 solutions out of this. All right, so I want to do one more problem, and it is by far the most challenging for everybody. And you know, usually they're something that'll be on tests, or sometimes they even put them on the basic skills test. But how do you solve an exponential when you have two different bases? And the answer is it's actually not that bad. It's just a lot of writing and you want to make sure you do the algebra right. So up until now, every expression like this we saw, we were able to either start with the same base and we could drop the exponents down, or we were able to turn one side into the other side's base, right? But 2 and 5 are prime. You're never going to make 2 5 and you're never going to make 5 2. That's never going to happen. So how do you deal with this? So since the x's are trapped in the exponent, the only algebra move that lets us bring them down is to use some kind of log. So this is where you have choice. You can use log base 2 of both sides. You can use log base 3 of both sides. Log base 5 of both sides, but all that's going to do is kill one of the bases for you, right? You could use log of both sides, but this is where I mentioned before that typically in this case where any log will do, we usually just use natural log, because if we're going to have to write it a lot, natural log's easy to write and it's easy to work with. So I'm going to take the natural log of both sides. But theoretically, any log I want to use would work here. All right, so then that lets me bring the exponents down. But this is where you have to be careful, because this is what gets people into trouble. These are expressions. These are not single terms. So the entire exponent, you have to use parentheses, is multiplied by natural log of 5. And same thing is true on the right. But I can guarantee you on a test, somebody will just write 3 minus 2x natural log of 5. And then when they go to do the next line of algebra, they keep the natural log of 5 with the 2x and they forget it belongs to the 3 as well. Okay? So then in order to solve for x, we actually have to distribute both sides. So on the left, we're going to get 3 natural log of 5 minus 2x natural log of 5. On the right, we're going to have 8 natural log of 2 plus x natural log of 2. So now it's just an algebra problem solving for x. So if I got to move all the x's to one side, I think I'm going to move them to the right because I have a negative 2x over here and I just want to make it positive to have positive numbers. So I'm going to move this term over to the right, which means I need to take this term and slide it over to the left because I just want the x's on one side. So 3 natural log of 5 minus 8 natural log of 2 is going to equal 2x natural log of 5 plus x natural log of 2. So you can kind of see already why these problems plague people, because you got to be really neat and organized and you're writing natural logs of 2s and 5s a lot. You want to make sure you get it in the right order. So we just slid this over here and slid this over here, right? So now on the right side, I have all my x's together, so I can factor an x out front. And then to solve for x, we divide by everything attached to the x. So if you really, really want to get good at your algebra involving these problems, I would practice solving equations like this, because you got to be careful with your parentheses, you got to make sure you're writing things down right, you got to make sure you're distributing. So solving exponential equations with two different bases that you can't convert from one to the other is really, really good practice, because it forces you to use all of these algebra rules. But these are the problems that tend to plague people because they just get careless with the algebra and they lose a lot of points. But these are pretty popular problems to assign. All right, so we'll